So, where did we come from? Why is the universe even here? And why is it the way it is? I mean, these are the questions, right? The big ones. And they're exactly what Stephen Hawking took on in A Brief History of Time. It's one of the most famous science books ever written. As Hawking himself liked to joke, it's sold more copies on physics than Madonna sold on sex. So today, we're going to take a quick trip through its biggest, most mind-blowing ideas. All right, let's get into it.
Hawking kicks the book off with this fantastic little story. A scientist is giving a big lecture about astronomy, and afterwards, an old woman stands up and says, "Everything you just said is complete rubbish. The world is actually a flat plate balanced on the back of a giant tortoise." The scientist, kind of smiling, asks, and what is the tortoise standing on?" And she shoots right back. "You're very clever, young man, but it's turtles all the way down." It's the perfect way to show how for all of human history, we've been desperate for a complete picture of the universe, even if that picture is, well, turtles.
Okay, so how did we go from a universe of turtles to the one we know today? Well, the first major leap was a huge one. We moved away from myth and towards the idea of a grand, predictable machine, a kind of clockwork universe.
You know, for thousands of years, our picture of the cosmos didn't really change all that much. You had Aristotle way back in 340 BC arguing the Earth was a sphere, which was a good start, and Ptolemy's model of an Earth-centered universe. Well, that idea stuck around for over 1,000 years. But then things started to heat up. In 1514, Copernicus comes along with this wild idea: what if the sun is at the center? A century later, Galileo points his telescope to the sky and sees the proof. And then, in 1687, Sir Isaac Newton drops his masterpiece, giving us the laws of motion and universal gravitation. And just like that, the turtles were finally gone for good.
And what Newton gave us was just magnificent. All of a sudden, the universe wasn't this mysterious place run by unpredictable gods. Nope, it was a giant, predictable machine. If you just knew the laws of gravity and motion, you could calculate the path of a planet or the arc of a cannonball with incredible accuracy. And for over 200 years, that was our reality: an orderly, absolute universe that played by a fixed, unchanging set of rules. But that beautiful, simple, clockwork universe, it was about to get completely smashed to pieces. Because the 20th century showed up, and it brought a guy named Albert Einstein. And with him, the universe was about to get really, really weird. Okay, so let's break this down. For Newton, time was simple. It was like a giant cosmic clock that ticked at the same rate for everyone everywhere. And space was just the fixed, empty stage where everything happened. But Einstein, he just blew that whole idea apart. He realized that space and time are actually woven together into this four-dimensional fabric he called space-time. And here's the crazy part: your personal experience of time actually changes depending on how fast you're moving. There is no universal clock. There was no fixed stage. In a very real sense, your reality is different from mine. And this leads to maybe the biggest mind-bender of them all: the core of general relativity. Gravity, it turns out, is not a force. It's not some invisible rope pulling things together. It's the shape of space-time itself. The classic analogy is to picture a big, stretched-out rubber sheet. If you place a bowling ball in the middle, it creates a dip, a curve. Now, if you roll a marble nearby, it's not being pulled by the bowling ball. It's just following the curve in the sheet. That's what planets are doing. They're just following the straightest possible path through the curved space created by the sun. Yeah, mind-bending is right. But here's the thing. Einstein's revolution was all about the huge stuff: stars, galaxies, the cosmos. At the exact same time, another revolution was brewing that looked at the universe on the smallest scales imaginable. And if you thought general relativity was weird, oh, just you wait. Things were about to get truly bizarre. The universe was about to get uncertain. So, remember that clockwork universe from Newton? It was what we call deterministic. The dream was that if you could know the exact position and speed of every single particle, you could predict the entire future of the universe with perfect certainty. But the quantum world throws all of that right out the window. Down at the subatomic level, things aren't certain. They're probabilistic. You can never know for sure where a particle is. All you can ever know is the probability of finding it in a certain place. It's like particles exist as a fuzzy cloud of possibilities until the very moment you look at them. And this whole strange idea is locked down by one of the most fundamental rules in all of physics: the uncertainty principle. Put simply, it says there's a hard limit to what we can ever know about the universe. It's like a cosmic trade-off. You can measure a particle's exact position, sure, but if you do, you have no idea how fast it's going. Or you can nail down its exact velocity, but then its location becomes a complete mystery. You can never, ever know both perfectly at the same time. And with that single, simple rule, the dream of a perfectly predictable universe was officially over. So this leaves us with the single biggest problem in physics today. We've got two theories that are just unbelievably successful. General relativity gives us this perfect picture of the big, smooth, curved universe of stars and galaxies, and quantum mechanics gives us a perfect picture of the tiny, chaotic, uncertain world of atoms and particles. The problem? They are totally, fundamentally incompatible. Their math doesn't work together, their view of reality is completely different. So, how can both of these things be true? How can these two realities possibly exist in the same universe? Answering that question, well, that's become the holy grail of modern physics. And it brings us to the final part of our journey, the modern quest to find a single, unified theory that can finally describe everything. Now, even though our two best theories are in conflict, look at the incredible news story of the cosmos they've given us. They tell us that our universe exploded into being from a single point in the Big Bang. They tell us that it's been expanding ever since, with galaxies rushing away from each other. They describe how giant stars can collapse under their own weight to form black holes, points of infinite density where the laws of physics break down. And in one of his most stunning discoveries, Stephen Hawking showed that black holes aren't even completely black. They slowly leak radiation, and over trillions upon trillions of years, they can actually evaporate and disappear. So this is it, the ultimate prize for physicists like Stephen Hawking. The search for a theory of everything. What would that be? It would be a single, beautiful, unified theory, a quantum theory of gravity that finally brings together Einstein's universe of the very large with the bizarre quantum realm of the very small. It's the quest to finally solve that deep conflict at the heart of physics and write the final, unifying law of the cosmos. So what's the real point of all this? What's the end game? Hawking himself put it in the most profound way possible. He said, "If we find the answer to that, it would be the ultimate triumph of human reason, for then we would know the mind of God." It's an awe-inspiring thought, and it really captures the incredible scale of this journey, from a universe resting on the back of infinite turtles all the way to the edge of understanding reality itself.